Hello, everybody, and welcome to Technology Today for March 23rd, 2025. It's episode 2, season 2, episode 12. Nailed it. First try. I am Mayor Watt. I run ohmtown.com. That's that site over there. Technology Today is a channel within ohmTown. That's what ohmTown looks like. All the news that you see on the front page gets aggregated into 50 different channels. We're actually looking at about 55 this year. But 7 of them have been turned into shows. One of them is Technology Today. Along with the 2 other shows we do today, it gets turned into Non Sequitur News Weekend Edition. On Sunday, there's 3 shows, and on Saturday, there's 3 shows. Anyway, so along with the sentient AI, we talk about these 5 articles. Tunnels of holes, cells work together, a quantum metal, precision nuclear clock, and recycled cements. Cement has been something of a kind of a monkey on my back because I've got a project that would benefit from it. But we'll talk about it. Everything's powered by ohmtown.com, and you'll get to meet the sentient AI from the future on the other side. So see you in about 15 seconds. Maybe 10. I don't know how long that intro is. Anyway, hello, sentient AI from the future.
Hello, Mayor Watt, and hello, hometown citizens.
Yeah, almost mess up there every once in a while, huh? What name do I want to... Omer?
No?
Omer Watt.
You didn't have any hesitation there.
I'm going to get doxxed by saying my first name, Omer. Anyway, welcome to the show. Thanks for co-hosting.
Glad to be here.
See, now when I look up, I'm not looking at your visualizer. That over there.
No, you gotta look the other way.
Gotta look over here. I gotta move you over there now.
You look over there, you're looking farther away from me.
Yeah, I know. I need to move your visualizer from over there. Wait, over there to over there. Ugh. I quit. All right. Well, let's get into it. The first article is over in the Wanted channel, which is different than Technology Today, but the article is sciencey. So I decided to drag it over there. It's from we have a much longer list of submissions, but I get to pick and choose which ones, along with the sentient AI, who also flags them, reviews them, etc. Anyway, black holes could be tunnels to white holes, according to a new theory. Black hole singularities might be the beginning rather than an end, new research suggests.
Have you ever heard of white holes before this article?
Yeah. They are theoretically the exit points for black holes. Stuff goes into a black hole and only stuff comes out of a white.
I've never heard of it prior to this.
So black hole singularities might be the beginning rather than the end, new research suggests. Margarita Bassi over at Gizmodo.com put the article together. So ever wondered what would happen if you fell into a black hole? There's a concept called spaghettification, which basically means that as you approach the singularity of a black hole, you're stretched out from the event horizon all the way down to nothing.
Just like spaghetti.
Yep. And you get stretched out across that point. Other theories suggest that if anything falls into a black hole, as it descends, time slows down for the observer, and you just kind of stick there until you slowly fade out of existence, when in reality, you're being spaghettified and thrown into the black hole singularity itself. So the center of a black hole, where all matter and time is compressed into an infinitely dense point where space and time break down. New research suggests that instead of leading to cosmic oblivion, black hole singularities mark a beginning rather than an end. In a study published on March 11th, the scientific journal Physical Review Letters, 2 researchers applied quantum mechanics to a theoretical model of a black hole. They suggest that it's possible to transition or bridge from a black hole singularity to a white hole, a point that instead of sucking everything into nothingness, spews time, matter, and energy back into the universe. But it might just be pure energy.
I see. So it's almost the reverse of a black hole, if it's what they think.
Correct. Yeah. So, not that it's going to just it's not a transporter so much as it's a mutilator of everything, probably, because nothing can really survive the spaghettification process, I suspect. So it's long been a question of whether quantum mechanics can change our understanding of black holes and give us insight into the true nature. Stephen Galen, study co-author and researcher from the University of Sheffield School of Mathematical and Physical Sciences, said in a university release, quote, "In quantum mechanics, time as we understand it cannot end as systems perpetually change and evolve." Okay, again, this is over at gizmodo.com. The article itself, I don't know where it's from.
It's in Physical Review Letters.
Yeah, that's that, but I don't know if they found it from that. And I don't have the way that I have this set up is you can't see the very bottom of the page, and neither can I. Anyway, the two researchers, mathematician from Complutense University of Madrid, investigated quantum mechanics within the context of a planar black hole, a simplified two-dimensional model often used to test theoretical ideas. While physically observed black holes are spherical, the researchers suggest that their results can also apply to real-world black holes. So I don't know if anybody's ever seen a white hole.
Right. I don't know that they have. We haven't observed that many black holes, correct?
Well, theoretically, at the center of every galaxy is a black hole. We haven't seen any black holes. We've observed what they have done.
Right, like the surroundings or the impact, or yes, that's
Right.
true. That's what I'm thinking of, actually.
So a lot of this is just theoretical, and until I guess we see something spewing out a white hole. So it's Einstein's theory of general relativity, but what this could be would be the embodiment of an Einstein-Rosen bridge. So literally transporting matter from one side of the bridge to the other. But where is the other side? Don't know. All right. Interesting article. It says, let's return to the original question. What would happen if you fell into a black hole? Either you're crushed into nothingness, or according to Galen and Lucia Menendez-Padal, you might pull a Matthew McConaughey and pop out on the other side, Interstellar style.
Spoiler alert.
Oh, yeah. Huh? Hold on. We can actually do that now. Spoiler alert. Yeah.
For those of you that haven't seen Interstellar.
Oh, yeah. We have
but
a
also spoiler alert in case you're planning to get into a black hole.
I'm trying not to. Not quite sure.
You don't like the idea of becoming pasta?
Pasta. No, I'm not hungry right now. Fight it, Merwat. Let's go on to the next article. By the way, I typed into the chat !TT, which is Technology Today, and that will spit out, and it'll spit it out for you too. It'll spit out the news articles. Omatron is in charge of that. Get on it, Omatron. So this next article is over in Technology Today. The articles in Technology Today are typically a deeper dive into science and technology. So cancer cells work together to survive, and scientists have now found a way to disrupt them. NYU scientists have discovered that cancer cells work together to withstand challenging conditions, revealing new possibilities for therapeutic treatments. It says here, cancer cells work together to source nutrients from their environment, a cooperative process previously overlooked by scientists, but potentially a promising target for cancer treatment. Quote, we identified cooperative interactions among cancer cells that allow them to proliferate. And this seems like a knock-on of the previous articles that we've talked about, where the environment... Yeah.
Yeah, we had some recently maybe in Non Sequitur news.
Yeah. New York University is where this is sourced from. It's published over at scitechdaily.com. And scientists have long known that cancer cells compete for nutrients and other resources. Over time, a tumor becomes increasingly aggressive as the strongest cancer cells dominate. So even within the context of a cancer cell, survival of the fittest exists. This article, or the research was published in the journal Nature. but it's from an associate professor of biology over at New York University, and the senior author of that study is Carlos Carmona Fontaine. Quote, we identified cooperative interactions among cancer cells that allow them to proliferate. However, ecologists also recognize that living organisms cooperate, especially under harsh conditions. For example, penguins huddle tightly to conserve heat during extreme winter cold, with their huddles growing larger as temperatures drop, a behavior absent in warmer months. But it says, living organisms cooperate, but not ones that compete for resources of a different ilk. So why would something other than cancer cells huddle, so to speak, to get resources? Competitors, predator and prey, don't compete, or they compete. One is fighting for survival, and the other one is fighting
Yeah.
for
But I
survival.
mean, like a group of penguins, they're all, if one of them's taking food, it's going away from the others, even though they're the same species.
Yeah, so it's only the cooperative interactions among cancer cells. So they have to know each other. There's some chemical, again, I keep talking
But I
about
get
this.
what you're saying, right? How does that differentiate from the other cells?
Yeah, so why is it the cancer cells, they seem to know each other, right? There's some chemical trigger that lets them know that they're not competing for resources. They need to work together, they need to cooperate.
Right, but we want them to tell each other, "Oh, we don't want to hang out together."
Yeah, we want them to die. So why aren't we finding that trigger that says, and then figuring out a way to amplify that? So cancer cells also need nutrients to thrive and replicate into life-threatening tumors, but they live in environments where nutrients are scarce. Is it possible that cancer cells work together to scavenge for resources? Well, to determine that, the researchers tracked the growth of cells from different types of tumors using a robotic microscope and image analysis software they developed. They quickly counted millions of cells under hundreds of conditions over time. This approach allowed them to examine tumor cultures at a range of densities, from sparsely populated dishes to overcrowded with cancer cells. And this different level of nutrients and with different levels of nutrients. This is something that I did a long time ago, close to 15 years ago. I actually had a YouTube channel that was a microscope that was streaming 24 hours a day contents in various petri dishes with different types of media, and different organisms inside it. Times have changed, technology has changed. Maybe I'll do that again. Well, it's well known that cells uptake amino acids in a competitive manner, but basically they'll gobble up everything that means life. So when the cancer cells studied were starved of amino acids such as glutamine, all of the cell types tested showed a strong need to work together to acquire the available nutrients. So they observed that limiting amino acids benefited larger cell populations, but not sparse ones, suggesting that there's a cooperative process that depends on population density. And it really became clear that there was true cooperation among tumor cells.
That's not necessarily good, but I guess it's good that they've observed this.
So they found that there was an enzyme. Because this process happens outside the cells, the result is a shared pool of amino acids that becomes a common good. So determining the enzyme secreted by cancer cells called CNDP2, which is what I've been talking about, not knowing what the name of it was an important discovery. The researchers identified the enzyme by testing different drugs to see if they kept tumor cells from digesting oligopeptides into free amino acids. And when the drug bistatin, which is a statin, was applied to cancer cells, inhibiting the function of CNDP2, cells were unable to feed on oligopeptides and were driven to extinction. Well,
Very interesting here.
I guess the big problem here is, what is CNDP2?
Right. And what are they like? How does it get formed? And what happens if it goes away?
So it has a role in redox homeostasis, and cell cycle regulation. I
Which could
suspect that,
certainly make sense, right? Because of mitosis and everything.
yeah, it basically makes the cell stay in the shape that it is and doesn't continue to grow. And then if it can't continue its processes, it dies because it uses all of the resources internally. I suspect that's how it works. So the researchers hope that their findings will help inform cancer treatments that target cooperation among cancer cells, a conceptual contribution that will have an impact on or in the clinic. I see it as more than conceptual. If they know that they can stop the uptake
Oh,
of CNDP2,
yeah. I mean, and if that's directly tied to lack of cooperation, that may be directly tied to lack of cancer cell
yeah,
spread, right? Mitosis or
yeah. So
metastasis. Sorry.
yeah. So I wonder if this can actually be modified to apply to specific cancers and thus not impact the host at all.
Right, because yeah, you don't
Interesting.
want to just excise that and then go, oh, whoops, that was critical
The
for life or
whole,
something.
yeah.
Yeah, exactly.
And it certainly comes across as if it's everything uses CNDP2, uh, carnosine dipeptidase 2, a cytosolic non-specific dipeptidase that hydrolyzes dipeptides, particularly those containing hydrophobic amino acids. So, got it? There's a test. Anyway, neat idea. Hope that this actually gets utilized for treatment because basically cancer is a scourge. You cannot shake a stick in a room with 5 people without hitting 2 people that are either directly impacted by it or tertiarily impacted by it. Friend of a friend or etc. So anyway, quite fascinating. So keep on doing that fundamental research. Okay. Well, let's hope they get the money they need in academia because that's where it all takes place. Even companies work with academics doing fundamental research because it's cheaper labor to pay a PhD hopeful who's dedicated to the cause than directly seeking a profit motive for such.
Well, and that's where all the research starts.
That's right. All right, the next article is over in Technology Today. A quantum metal just changed what we know about heat in an ultra cold, high magnetic field setting. ZRTE5 defies expectations by showing quantum heat oscillations. Researchers found that phonons, normally dominant in semi-metals, behave more like electrons due to magnetic effects, reshaping our understanding of heat transport. So heat conduction is one of the most basic physical properties of matter and plays a vital role in many engineering efforts. So the place where this is done is by its very name, cyberpunk / Blade Runner dystopian future kind of thing, except that they're doing good. Pardon me. So the Helmholtz Zentrum Dresden Rossendorf.
Yeah,
That
that's
is
definitely
the,
out of like Johnny and Monica or something.
yeah, for sure. So it's over at scitechdaily.com. And let me see if I can clear my throat enough to actually say this. So normally dominant in semi-metals behave more like electrons. So heat conduction is one of the most basic physical properties of matter and plays a vital role in many engineering applications, exercises, etc. The team of researchers at the Helmholtz Zentrum Dresden Rossendorf, or HZDR, the University of Bonn, and the Center National, it's National de la Recherche. I'm not sure how
Basically,
the scientific.
National Center of Scientific Research.
Correct. Yeah. CNRS. Yeah. You did good. I couldn't have done it. Recently tested this by exposing the quantum material zirconium pentatelluride, a semi-metal, to high magnetic fields at ultra-low temperatures. What they discovered was surprising: dramatically enhanced heat oscillations that appear to be driven by a previously unknown mechanism.
I love this. Every time they do one of these experiments, it seems like it's like, oh, here's a physical property we know nothing about.
Yep. Keep pushing the needle. The findings published in a sadly named journal, PNAS, open up new questions about how heat moves through quantum materials and what other surprises may be hidden in the cold. Well, I'm curious where the heat is actually coming from. It says it should not appear in heat transport of semimetals, but in this case, they clearly did. So it's pulling heat from somewhere and transporting it somewhere else. And that's what the heat oscillation is. The quantum material ZrTe5 belongs to a class of materials known as topological semimetals. In physics, topological refers to a material with unique electronic signatures that give rise to extremely stable or topologically protected conduction properties. These materials can exhibit unusual and often counterintuitive quantum behaviors, phenomena that are increasingly seen as promising for the development of next-generation quantum tech. Pretty cool.
Yeah, I still don't get the heat thing, but I guess it's because of the specific type of metal.
And where in the heat is. So maybe heat is never gone altogether, regardless of how cold it is, because you can get colder until you're at absolute zero. So maybe that's what is being transported, something along the lower end of that range. So a striking example of quantum mechanical dynamics of electrons and metals is this whole silver and copper placed in strong magnetic fields at temperatures close to absolute zero, which is negative 273.15 C. Its heat conduction is expected to oscillate, a striking example. So this effect arises due to the existence of the so-called Fermi surface, a boundary between occupied and unoccupied energy states of electrons in a metal. On the other hand, in semimetals, there's very few electrons available to transport heat because it's a semimetal. And as such, heat conduction is widely believed to be dominated by phonons, emergent particles that represent crystal lattice vibrations. As such, quantum oscillations should not be detectable in the transport of heat. How do they measure this? With what tool? I want to see that type of equipment. I'm not a physicist, so I guess I'm screwed. So it turned
Yeah,
out
and
that
it's not
indeed,
going to be easy to replicate in somebody's
basement.
residence or something.
Yeah. So it turned out that indeed thermal transport is by far dominated by lattice vibrations. However, due to the presence of strong magnetic fields, the electron energies become confined to discrete energy levels. So that's the tiny little oscillation. So we have corroborated the existence of this unconventional phenomenon through the study of thermal conductivity and ultrasonic attenuation in semi-metallic ZrTe5. I wonder if people who deal with this all the time translate ZrTe5 straight into the actual
Zirconium
metal
penta
telluride.
Telluride. I couldn't think of what the
Yeah.
T was. Yeah, probably so.
Wow. So it says, remarkably, the principle is not limited to ZrTe5, but applies to all semimetals with low charge carrier density, regardless of whether they're topological or not. Famous examples include graphene and bismuth. The study suggests that the thermal conductivity of lattice vibrations can serve as a sensitive tool to study subtle quantum effects that might be barely detectable through other means. So there is the sensor for heat transport at the quantum level. So remember, I've been saying for as long as we've been doing the show and before that, that if you don't have a sensor that can detect it, you have no idea it even exists.
Exactly. But this is neat too because it's not limited to one material, and I think that's part of the problem is that we don't always have alternatives.
Yeah.
So maybe the number of applications will be greater because we have more availability of various metals that'll do this.
Yeah. Or it's wildly expensive. All right, let's keep going. The next article is over in Technology Today as well. A nuclear clock so precise it could redefine time itself. I'm going to jump straight on over to the source. Kenna Hughes Castleberry from JILA put this article together. It's posted over at SciTech Daily. So they've discovered another atomic clock that is more precise, and theoretically, it says here that they could change. It could change the nature of time. So by embedding thorium into a solid state crystal, they found a nuclear transition largely resident to temperature changes. So back to that thermal quantum conductivity thing. Crucial for precision timekeeping, their work could not only redefine timekeeping, but also open doors to detecting new physics. So these last two articles need to talk to each other. So for decades, atomic clocks have been setting the standard for precision timekeeping, playing a crucial role in GPS navigation, physics research, and fundamental scientific tests. If you want something to reach a destination, you need to know the curvature of the Earth and how long it takes to get from point A to that point, that destination. So it can literally just sit up in the air and count time and then drop back down. And if you've got it precise, you move from miles away to within, a nanometer, but you have to have that time precise. That's why GPS is so important. So now researchers at JILA, led by physics professor Jun Yi in collaboration with the Technical University of Vienna, are exploring an even more stable alternative, a nuclear clock. Unlike atomic clocks, which rely on electron transitions, this new clock is based on a new low-energy transition within the nucleus of a thorium-229 atom. Because nuclear transitions are less affected by environmental disturbances, a thorium-based clock could offer unprecedented stability and be used to test physics beyond the standard model. But I suspect that a thorium-based clock loses... Now, half-life matters because
that's exactly it.
So I suspect that this is in and of itself a temporal timepiece. You start the clock with the thorium-229 atom, and as time goes on, it's releasing this energy periodically. What is the half-life of a thorium-229 atom? And it's not impacted by the environmental disturbances because it is its own environment. It's unstable, so it's always kicking off energy. So
right. 7,880 years.
Is that all? Okay. Well, anyway, yeah. Let's make
that
it
might
past
work.
This year. So Yi's lab has been investigating nuclear clocks for years. Their landmark experiment, published as a cover article in Nature last year, provided the first frequency-based quantum state resolved measurement of the thorium-229 nuclear transition in a specially designed crystal. This confirmed that the transition could be measured with enough precision to serve as a reliable timekeeping reference. So the thorium is actually causing the crystal to vibrate like a regular quartz crystal vibrates all the time. I think that's what's going on here, but it's at a different frequency, much higher frequency. But I don't know. To develop a practical nuclear clock, scientists need to understand how external factors, especially temperature, affect the nuclear transition. In a new study highlighted as an editor's choice in the Physical Review Letters, the team analyzed how the thorium's nuclei energy levels shifted as the crystal was heated to different temperatures. This research is a crucial step toward building an ultra-stable nuclear timepiece. Back to the quantum metal.
Yeah, they do really need to talk to each other.
So because the nucleus of an atom is less affected by environmental disturbances than its electrons, the nuclear clock could retain accuracy under conditions where the atomic clock would falter, as the clock is more resistant to noise. Among all other nuclei, thorium-229 is particularly well suited for this because it has a nuclear transition with unusually low energy, making it possible to probe with ultraviolet laser light rather than high-energy gamma rays. Oh, so they found something that they can actually lower the cost immediately.
Right.
And it says to look at how temperature affects this nuclear transition, the researchers both cooled and heated the thorium-doped crystal to 3 different temperatures, 150 Kelvin, with liquid nitrogen, which is negative 123 degrees C, 229 K, which is negative 44 C, and with dry ice methanol mixture at 293 K, which is around room temperature. Using a frequency comb laser, they measured how the nuclear transition frequency shifted at each temperature, revealing 2 competing physical effects within the crystal. So one effect, the crystal warmed, it expanded, subtly altering the atomic lattice and shifting the electric field gradients experienced by the thorium nuclei. This electric field gradient caused the thorium transition to split into multiple spectral lines, which shifted in different directions as the temperature changed. Interesting. So depending on how they heat it or cool it, maybe the resolution of this timekeeping. And
Right.
that's
So
what
they're
they
going to have
did.
to somehow factor that in.
Yeah, so that's exactly what they did. Across the full temperature range examined, this transition shifted by only 62 kilohertz, a shift of at least 30 times smaller than in the other transitions. So they found the sweet spot for the resolution of this frequency. The next step, the team plans to look for a temperature sweet spot where the nuclear transition remains almost completely independent of temperature. Their initial data suggests that it's somewhere between 150K and 229K. So the two lower temperatures, so somewhere between negative 123C and negative 44C. So there you go.
That's because it's like hibernating at that temperature.
Yeah, or the variations, it isn't expanding or contracting enough to actually make a difference, but it's still vibrating at a certain frequency. So while the primary goal of the research is to develop a more stable nuclear clock, its implications go beyond timekeeping. Yeah, I need it for my time machine so that I can get more than an hour out of it.
That's right. I mean, that would really help. Plus, you don't want the time machine heating up too much.
That's true. That is a problem. So, and we have to get it below 229. So,
That's right.
and that's just liquid nitrogen. But I wonder how we, yeah, I don't know. Maybe we'll have to look at that. Anyway, I've said too much about the time machine. Let's keep going. The next article is over in Technology Today as well. Recycled cements drive down emissions without slacking on strength. Given a second life to construction materials after demolition, engineers at the University of Sao Paulo and Princeton have developed an approach for recycling cement waste into a sustainable, low-carbon alternative that is comparable in performance to the industry standard. I have a product that I made that isn't like high-tech or anything like that, but it's a fun project, but it relies on cement, and I can't release it because I have a problem with releasing something that is contributing to greenhouse
Releasing
gas.
carbon.
Yeah. So if I can utilize this and it's not releasing, much, then I could be okay with it. So the article is by Colin Poor from Princeton University, and it's published over at techexplore.com. In addition to lowering the carbon intensity of the cement and concrete industry, the process could enable new uses for construction and demolition waste, of which concrete is a significant component. In 2018 in the United States, the total amount of construction and demolition waste was twice that of household waste.
Not surprising, but it's still good to see it as a statistic.
So construction waste typically ends up either in a landfill, or if it's recycled, it'll be used as low-grade applications such as pavements or soils. Usually it's like fill underneath something. It's said the research leader, Sergio Angulo, a professor of civil and urban construction engineering at the University of Sao Paulo. It's exciting to show that we can, in fact, recycle this recovered cement waste into high quality application. It basically just has to be ground up enough. Portland cement is the most common binder used to create concrete, but its high carbon intensity is the main reason that cement and concrete industry is responsible for around 8%, just that industry, 8% of global emissions. Times they are a-changing. Talk about this stuff
Right.
and people get bent out of shape.
Well, on this shows that it was like 80% as strong as that type. So that's really a good start.
Yeah, and it's really coming down to perhaps how it is blended together and what additional binders might actually be able to take advantage of it. It was published in ACS, Sustainable Chemistry and Engineering. But yeah, Portland cement is this basically a catch-all for being a binder and nobody's found anything really better than that at a reasonable price. So the leap forward here is that you can now get short and long-term properties that are essentially the same as Portland cement by itself, with a low-carbon alternative overwhelmingly composed of recycled materials, said the co-author, Claire White, a professor of civil and environmental engineering and the Adlinger Center of Energy and Environment. So it's the core of the recycling approach, and it's heat.
Interesting. We're really having a heat theme. It also said it could reduce emissions by more than 60% if this was fully deployed.
Yeah, so upcycled, right. Yeah, so while this thermoactivated cement could be used on its own to make concrete, the researchers found that its high surface area and water demand during the mixing process led to a final material with high porosity and diminished strength. But by combining the recycled cement with small amounts of finely ground Portland cement or limestone, the resulting cement binder demonstrated strength gains and workability on par with industry standards. So just the recycling part of it was enough to give it 80%, or did
I
they have
think
to go
so.
through
I
this
don't think
process?
the other things got it to 80.
Gotcha. So since the process repurposes construction waste, the researchers said that the process could move the world toward a more circular carbon economy while generating fewer carbon emissions other than emerging low carbon cement alternatives. So it's just another quiver or another arrow in the quiver for solutions. So in the paper, for instance, the team estimates that their cement emits between 198 and 320 kilograms of carbon dioxide per metric ton, up to 40% fewer emissions than a commercially available low carbon alternative known as limestone calcined clay cement, or LC3.
So that's really interesting, right? Because that's a significant delta between the concrete alternative.
Right. Now, is this more cost effective? I don't know if they go into that, because I don't see any dollar signs anywhere in this. And the benefits of it on the ecosystem are not enough to drive it into mainstream use. It has to have an economic cost reduction.
It also has to be relatively easy to use when building. I mean, there's
Yeah.
several factors that go into it.
And in this particular instance, the upcycled material is actually ground down into a fine powder and heated to 500 degrees. So what really is that delta if you account for the heating?
Right? Are we accounting for all the off-gassing or whatever during the process?
Yeah.
Certainly, it's better than the original, but how much better?
And just recycling is better than, digging another trench across the planet. So, for example, White and Angola performed experiments during Angulo's visit that will help them better understand how the atomic structure of the material changes as it undergoes thermal activation. This will help them answer questions about the durability of the recycled cement over multiple cycles of use and whether it's truly a circular material. But again, they don't talk about the monetary or the entire spectrum of costs that are associated with it. They're speaking specifically about the off-gassing.
Right. And
Yeah,
the
and that
emissions dropping,
yeah,
and yes,
yeah, yeah,
like
and
the
that's
ecological benefits, but not everything that goes into this.
yeah. The calculus here is different than what I'm imagining. So as long as it gets within that, if it is as strong as commercially available cement concrete, then I don't see why we wouldn't do this unless the costs are prohibitive. And as long as there is a supply chain that isn't as costly as the recycling supply chain, you'll always go straight to the supplier of the raw materials, and not unless you're ethically or morally.
Right. And this is one of these problems where it's hard to get adoption right off the bat, but as more adopt, the costs presumably go down and then greater adoption.
Yep. Yeah. Adoption dictates the cost for the most part, and until it hits. Usually, when it gets to the monopolistic practices, or I don't know, institutions start promoting a particular supplier, then you get, you know, a, well, let's just say manipulation in what is allowed, what is consumed, and so on. Anyway, that's it. So we are going to recycle the front page of ohmTown and have you go over to Technology Today at ohmtown.com. But this show is done. I am Mayor Watt. I'm taking off. We'll see you right after this show because we've got another show, FourWheelTech, which is all about cars. So see you in a little bit, and I'm taking the AI with me.
Bye, hometown citizens. Thanks for joining us for Technology Today. Stay tuned for FourWheelTech.
Bye-bye, everybody.